So hello everyone and welcome back. We have 4 minutes before class starts if anyone would like to ask me any questions. So I think we're going to have a small audience today because a good fraction of the people in this class are also in my COMP2402 class, which means that they're writing a midterm exam right after this class. Okay, so we're continuing now to talk about binary search trees that we discussed last class as one kind of binary tree, and that's a particularly important kind for this course. And I want to start by introducing you to this very nice notion of random binary search trees, and then using those to find a very efficient and simple implementation of the sorted set interface, or the simpler version of the interface called the S-set interface. So let's start with this example here. So here's a sequence of numbers. It's all of the integers from 0 through 14. And imagine we want to create a binary search tree that contains those numbers. And we'll do that just by starting with an empty binary search tree and then repeatedly adding the next number in the sequence until we have a binary search tree that contains all of these numbers. So the first number in this, so we start with an empty search tree. Here's a picture of an empty search tree. We start with the number 7, and that just creates a binary search tree with one node that contains the number 7. Next, we want to add the integer 11, and we went over this last class, but let me remind you, when you add something, you start at the root and you follow the search path for the thing that you want to add until you fall out of the tree. So here we start at the root, we compare 11 to 7, and 11 is bigger, so it means it's going to go in the right subtree, and we just fell out of the tree, so now we add the new node 11. Like so. Next, we want to add 9. We compare 9 to 7. 9 is bigger than 7, so it goes to the right, but it's smaller than 11, so it goes to the left. And then we fell out of the tree, so we add 9. Next up is 3. 3 is smaller than 7, so we go immediately to the left, and we're done. Next is 1, smaller than 7, smaller than 3. That takes us here, and we're done. Next up is 5. 5 is smaller than 7, larger than 3, so that takes us there. 8. 8 is larger than 7, smaller than 11, smaller than 9, so 8 goes, let me draw this nicely. 9 was here, so 8 will go here. Next up is 10. We go from 7 to 11, and then we fall out here at 10. Next up is 13. Bigger than 7, bigger, oh, that's wrong. 10, of course, is smaller than 11, so we go left at 11, and it's larger than 9, so we go right. Next up is 13. 13 is larger than 11, so that's where we put it. Next up is 0. 0 is smaller than 7, smaller than 3, smaller than 1, so it goes there. Next up is 4. 4 is smaller than 7, but larger than 3, but smaller than 5, so it goes there. Next comes 2. That goes here. Next comes 12. That goes here. Then 6 goes there. And finally, 14 is the last one. It goes there. Okay, so that's how we can create a binary search tree given any sequence of distinct numbers like this. And so for any sequence of distinct numbers, we can run this process, and we get a binary search tree. And there's a definition over on the board here that says, well, yeah, so the question is, is the root always the first element in the permutation? So when we're building a search tree, a binary search tree, incrementally like this, and we're going to do that because that's how we're going to define random binary search trees. Indeed, the first element will always be the root. It's the thing that goes in the empty tree. After that, every other element that you add will have to get compared to the root and go into the left subtree or the right subtree. So indeed, this will always be the root when we create a tree this way. And if this thing is a random permutation, meaning that of all of the n factorial possible permutations of these n items, if it's chosen uniformly at random, then you do this. And the thing that you get at the end is what we'll call a random binary search tree. Okay. So really a random binary search tree is a distribution over search trees, but we'll just think of if I built the tree by starting with a random permutation, doing all these insertions, then the tree that I get at the end, I'll call that a random binary search tree. Okay. So here we've seen an example of I'll say random binary search tree, starting with this random sequence, whatever a random sequence means. Here is a different binary search tree. So it's the binary search tree that has the root 0, right child 1, the right child of that is 2, the right child of that is 3, and so on. So there are no left children. And it's also possibly a random binary search tree, meaning if I give you the right permutation of these numbers, then this is the search tree that you'll get, and it'll only take you a few seconds to think about what the right permutation is. The observation starts with, well, the first thing in the permutation is always going to be the root. So the permutation that creates this thing is going to have to start with a 0. And that creates the tree that has only this one node with a 0. And then the only other node we can attach at this point to get this tree is a 1. So the next thing in the permutation is going to be a 1. And now we have this tree that has 0 and 1. And the only thing that's left to attach to this tree that we can attach at this point is a 2. And so you see that if I want to make that tree, then the permutation that I have to use is this one. It has to be the elements in sorted order. That's the only way that I can make this tree. Now if I look at this tree, that's not necessarily the case. So for example, here's a permutation that I used, and I got this tree. But here's another one that you could use. If I ran this whole process again, but I started with this permutation, which is definitely different from this one, right? The only thing that they really obviously have in common is that they both start with 7, but after that things get quite different. You'll see that I still end up getting the same tree. In fact, we can do the first few steps, 7, and then 3, and then 11, and then 1, and then 5, and then 9, and 13. And if I keep going, I'll attach all of these even numbers at the leaves here. Okay. So 2 examples of trees, both on the same set of elements, integers 0 through 14. But this one, there's only one permutation that creates this tree. And this one, well, there's at least 2 permutations that create this tree. So that means that if I take a random permutation, then the probability that I'll get this one, this tree, is only 1 out of n factorial, because there are, in this case it's 15 factorial, because there are this many permutations, and only one of them is the one that gives me this tree. On the other hand, if I calculate carefully, I can count the number of permutations which will give me this tree, and the number is 21,964,800. Okay. So it's not just the 2 that I've shown here. There are nearly 22 million different permutations which will generate this tree. Okay. And a couple of things to note. The height of this tree here, the unlikely tree, is 14. The height of this tree here is 1, 2, 3. Okay. So if I ask you, okay, if I take a random binary search tree with 15 numbers in it, what can you tell me about the probability of this tree versus getting this tree versus getting this tree? Well, I can tell you that this one is 22 million times more likely to occur than this one. So that seems to suggest that when you take random binary search trees, you're much more likely to get something balanced than you are to get something really unbalanced. So something, you're more likely to get something of small height than you are to get something of big height. And that's the idea. And why is that useful? Well, I think it's not too hard to see that this is not a great binary search tree. It's not very efficient, right? If I go searching in this tree, I am basically searching in a list. So if I look for the value x, then the number of steps that I'm going to have to take to get to x is actually x. So if I go looking for 14 in this list, I'll have to take 14 steps. If I go looking for 7, I'll have to take 7 steps. On the other hand, in this binary search tree, if I go looking for anything, I'll only have to take 3 steps. Doesn't matter what I'm looking for, I'll take at most 3 steps. Okay. So this is a better binary search tree. This is a worse binary search tree. And the nice thing is, if I take a random binary search tree, the better one is much more likely than the really bad one. And we can actually quantify that with the following theorem that I won't prove in this class, but I may prove in the other course that I'm teaching. Theorem. In any random binary search tree with n nodes, the expected, I shouldn't say any, in a particular one, the expected length of the search path for any value x is at most 2 times the natural logarithm of n plus 2. Okay. And this is approximately, natural logarithm is a weird one for us to work with. We tend to work more with binary logarithms. This is approximately 1.38 log base 2 of n plus 2. We can compare this with what we saw with skip lists. In skip lists, we saw 2 times log base 2 of n. These random binary search trees are a little bit faster on average. We get a 1.38 instead of a 2 here. Okay. Good. That's fantastic. So it says that if I just create a binary search tree this way by adding items in a random order, I'll get a search tree that's great. This is for any value x. You search for anything that's either in the tree or even if it's not in the tree, meaning you fall out of the tree. That's the expected length of the search path. So it sounds like, well, then binary search trees are easy. You don't have to worry about the height. It just takes care of itself. Unfortunately, that's not true. Because if you look at the bad binary search tree, the one that has all of it, that just turns into a giant list, what is the sequence that creates that one? That's this sequence. Now, this sequence is just the items in sorted order. And so you can imagine that if you just use a binary search tree in your application without thinking, worrying too much about it, and just taking the items in the order they're given and adding them, it's not that uncommon that you receive data that's already in sorted order. And if that happens and you insert it into a binary search tree this way, you're going to create that bad tree. Okay? So in real life, data is not random. Sometimes it's actually in sorted order. That's a fairly common thing. And so this theorem looks nice, but it's not that useful just like that in real life. Okay. All right, but we will see how to make use of it. So we're actually going to take binary search trees that are not random, but we're going to make them random. So we really want to support the sorted set interface, whose main operations are adding an element, removing an element, and finding an element, searching for an element. And so before I tell you the structure, let me just point out this picture here that I've been keeping up here. This is a picture of what's called a rotation in a binary search tree. So it's an operation that takes an edge. In this case, it's an edge with endpoints x and y in the tree. X is the child of y. And it does what's called a rotation about y. So in this case, x is the left child of y. So moving from here to here is what's called a right rotation. You can kind of see things are moving to the right. And once it's done, x is now a parent of y. So the edge xy is still there, but now x is the parent of y. And there were 3 subtrees in this picture that are marked as A, B, and C. They're still there. They don't get touched, but they sort of change their location, right? So A was the left child of x. Okay, it's still the left child of x. B used to be the right child of x, but now it's the left child of y. And C was the right child of y. Okay, it's still the right child of y. So B changes from being the right child of x to the left child of y, and x and y change their parent-child relationship. And you can check, right, if this thing here was a binary search tree, that means that everything in A is smaller than x, and everything in B is larger than x, but everything in B is also smaller than y, which is also smaller than everything in C. And when you go to this picture, that's still true, and everything is still in the right order, right? If you read this thing left to right, you see A, X, B, Y, C in the correct order. So if this is a binary search tree and I do a rotation, then the thing that I still have is a binary search tree. So I can still search in it and it will correctly find the things that I'm looking for. And sort of the main effect that we want to think of here is, what is this doing to x and y? Well, x used to be a child of y, now it's the parent of y, and in fact it's taken the place of y in the tree. So you can imagine this picture is embedded in a much larger tree. Y is the child of something in a much bigger tree than well, x takes the place of y. And in particular, x gets closer to the root. So it gets higher up in the tree. Okay, good. So let's now define something else. You have seen the binary search tree, what that is. So I want to talk about a different structure that we'll study as well a few times in this course. I'll call it a heap. And that is a binary tree where each node U has a priority call it u dot p, and it has a very special property, which is that for each node u except the root, u's parent priority is smaller than u's priority. This thing here is called the heap property. So it kind of smells a little bit like the binary tree property, but it's actually quite different. So for example, that's an example of a heap, because if these numbers listed here are the priorities, then what the heap property says is that everybody has a larger priority than their parent. Right? So 0.3 is larger than 0.1. 10,000 is larger than 0.3. 0.9 is larger than 0.3. 100 is larger than 0.2, and 7 is larger than 0.2. And so this basically, so we've just checked that this is indeed a heap because we looked for each edge to see if it had that heap property, which is all you need to check, and indeed it does. So this is a heap. So notice it's very different than a binary search tree. I can't search for things in here because comparing to the root doesn't give me any idea of whether the thing I'm looking for is in the left subtree or the right subtree. Perhaps the only thing I could conclude is if the thing that I'm searching for is smaller than the root, then I know it's not there. And why is that? Well, that's because if everybody except the root has a larger priority than their parent, you have to wonder then, okay, where does the smallest priority go? Because there's nothing smaller than the smaller priority, and so the only place that could go is at the root. I can't put the smallest value down here because this has a parent which needs to have a smaller value. So the smallest value always ends up at the root, the smallest priority. Yeah, so this is the definition of what's called a min heap. If you want a max heap, you just replace less than with greater than here. But we want a min heap. Okay, good. So that's a heap. We already know what a binary search tree is. So that brings us to the main topic of this lecture, which is a treap. And this is a binary search tree. No, it's a binary tree. Where each node has a value x and a priority p, and it has the following two properties. Let's call it t. T is a binary search tree with respect to the x values, and at the same time T is a heap. with respect to the p-values. Okay. So there's a lot to digest here, because you've just learned the definition of a heap, and now I'm telling you that a treap is somehow simultaneously a binary search tree on x values, and it's a heap on p values, priorities. And the first question you might ask is, well, wait a minute, is that always possible? So let's see if that's always possible. So, and let's do it with an example. Okay, so here I've drawn some nodes. Each one has a priority, so I'm going to use real numbers for the priorities, just so we don't get confused. So they're the ones that start with 0 point something. So the priorities, we'll say that they're real numbers between 0 and 1. And the values, or some people call them the keys, are the integers here. Okay. So in order to be a treap, I need to be a heap with respect to the priorities and a binary search tree with respect to the values. And well, if I look at this, if I want to turn this into a tree that has those two properties, I need to pick what the root will be. And there's only one choice for the root. Why is there only one choice for the root? Well, there's only one choice because this thing has to be a heap with respect to the p-values. And I already mentioned that in a heap, the smallest value is stored at the root. So to know which one of these is the root, I only have to look at the priorities and take the smallest one. So here's what has to be at the root because it's the smallest priority. If I don't put this at the root, I can't make a treap. I can't make a heap. So 0.19 is the node at the root. Now I need to decide what goes in the left subtree and what goes in the right subtree. But I don't have any choice, right? So what's going to go in the left subtree, because this thing has to be a binary search tree with respect to the x values, is everything less than 9. Right? 9 is the x value at the root, so everything less than 9 has to go in the left subtree, and everything bigger than 9 has to go in the right subtree. In this case, 9 happens to be the biggest thing, so there'll actually be nothing over here in the right subtree, but there's the left subtree to deal with. So I have already decided that this thing is the root. Now I have the left subtree, which contains all the other nodes, because they all have keys smaller than 9. I need to decide what the root of that subtree is. And again, the heap property says that the only option I have is to take the one with smallest priority. So here there's one with priority 0.2, that's the smallest one. And it has the key 7, so it goes there. Now I need to know what goes in the left and what goes in the right. Well, On the right here is going to be everything bigger than 7 and smaller than 9. On the left is going to be everything smaller than 7. So those are, for example, over on the left here, stuff that's smaller than 7. And over on the right here, stuff that's bigger than 7. There's only 8. So if I look on the right, let's do that one first because it's the easiest one. There's only one option. It's that node, 0.48. Now there's nothing to put to do here. And over on the left, I have these 3 green nodes, all with values smaller than 7. And I need to take the one with the smallest priority, and that's 0.3. And it's holding the value 4. And then on this side has to be everything bigger than 4, which is 5 and 6. And on this side there's nothing because there's nothing smaller than 4. And so out of 5 and 6, which one has the smaller priority? It's 0.7. And then finally, the last thing we have to add is this node, which has to go to the left, or to the right of 5 because it's larger than 5. And it has priority 0.9. And I think that this convinces you that no matter which values and which priorities I give you, as long as they're all distinct, so no 2 priorities are the same and no 2 values are the same, you can build a treap that works for those things. And the algorithm is simple. Find the smallest priority and make it the root. And then look at all of the other nodes. The ones whose key is smaller than the root, they will recursively go into the left subtree. And the ones whose values are larger than the root, they will recursively go in the right subtree. So feel free to ask a question at any time. I'll proceed in any case. So you give me any set of these things, and the treap exists. And that's good. Now, let's define something else. A random treap. Well, a random treap is just a treap in which the priorities are, all right, random, let's say real numbers. From the interval 0, 1. I'm just saying that here because I want a nice way to write, to be able to distinguish priorities from keys. So keys for us will be integers in these examples, and the priorities will be real numbers. But in fact, the priorities can also be random integers from a big, big set. You know, take all of the 4 billion 32-bit integers and use those, a random subset of those as the priorities. That also works. Okay, so that's the definition of a random treap. All right, so what? What is the purpose of that? Well, so random treap says, yeah, it's just a treap, but the priorities are picked at random. Let's think about this another way. Let's take these things here and we'll sort them by priority. So if I sort them by priority, the first one is 0.1, the next smallest priority is 0.2, the next smallest priority is 0.3, The next one is 0.4. The next one is 0.7. And the next one is 0.9 with key 6. This is the same set of nodes. I just sorted them by increasing priority. Okay. And now look at what happens. If I add these things to a binary search tree in this order, using the keys, then yeah, the first thing is this. Then I have to add 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 this. 0.75. And then I have to add this. 9. Look at that. That's the same tree. In fact, that's not a coincidence. That had to happen. If you just think about it for a few minutes, the treap, the way we built it is we took the smallest priority and we put it at the root. Well, when we sort by priorities, the first thing in the sequence is the one with smallest priority, and when we create a binary search tree by adding things, the first thing in the sequence becomes the root. So the two are certainly going to have the same roots. And then after that, well, everything that is smaller than the root will have to go in the left subtree, and everything that's larger in the root will have to go in the right subtree. And those are built recursively the same way. So you can think of a treap as either this thing that's defined this way, or equivalently, if you give me all the priorities and the values first, I can just sort by priority and then build the tree incrementally the way that I've been doing it. So that's another way to think of a treap, as sorting by priority and then just adding the nodes. But wait a minute, if a random treap is when you give random priorities, and a random binary search tree is what happens when you add things in a random order, well, if I give random priorities to these things and then I sort by priority, that means the keys are in random order, right? So if the priorities are truly random, that means when I sort them, I'm equally likely to get any permutation of the keys, which means it's a random permutation of the keys. Okay. So here's the point. A random treap is a random binary search tree. So I don't know, this is an observation. A random treap is a random binary search tree. Because it has exactly the same shape we would get if we, the same distribution of shapes we would get if we just took the keys, sorted them, ordered them randomly, and then inserted them one after the other. But instead of ordering them, doing it that way, instead we gave them random priorities and then made sure that they had the heap property. But we get the same thing in either case. And that has a consequence. The expected length of the search path for X in a random treap, is at most 2 times the natural logarithm of n plus 2. Just because random treap is a random binary search tree. So you just take the statement about random binary search trees, and now you can replace random binary search tree with random treap. So I guess I should quantify what's n. This is an n node random tree. So n, as usual, is the number of data items in the structure. Okay, so someone says, would it be an issue to have the same value but distinct priority, or 2 with the same priority but different values? Yes. So you can have the same value twice, and you can have the same priority twice. Nothing will break. You have to make some arbitrary decision about what you do when you have 2 keys with equal priority, because at some point you have to choose one of them to be a subtree, to be the root of some subtree. That means the other one has to go lower. So that's what happens if you have equal priorities. And if you have equal keys, then you have a similar issue that one of them has to be the parent of the other, basically. So one of them has to go first, and the other one you have to decide whether it goes to in the left or the right subtree of that one. But 2 things. One is, since we're going to use these to implement sorted sets, we don't have to worry about equal keys, and we don't want to have to deal with equal priorities because, well, we can usually get around them by just taking random priorities from a huge set, so that it's just very unlikely that you'll get 2 equal priorities. So we don't worry about that, and we don't actually want equal priorities, because it would be really bad if all the priorities were equal. Then basically whatever your rule is for breaking ties becomes the rule for how the treap is, the shape of the treap. And usually that rule is something simple, like, well, I don't know, maybe then you go to keys, but actually then a simple rule might give you the bad tree in that case, so the tree that's just a giant path. Someone else says, I could see this useful for indexing based on how often you plan to look it up. That's an excellent observation. In fact, the original paper on treaps, one of the things that they discuss is not choosing these priorities completely at random, but if you have keys that you think are going to be accessed more frequently, you choose a priority which is smaller for those keys. And in general, that means that those smaller priorities, they're going to be the ones that are higher up, closer to the root, and therefore faster to search for. They'll have shorter search paths. We won't talk about that, but that's an excellent, excellent observation. Okay, good. All right, so still, why all of this? Why do we care? Well, remember, we want to implement the sorted set interface. Add, remove, and find. Okay? And we're going to do that with a treap. So we have add, remove, and find. And find means find the value x if it's there, or find the smallest thing that is larger than x if it's not there. Different variants, depending on exactly what behavior you want for things that are not there. But this one, we already know how to do, right? This is just search in a binary search tree. So just follow the search path for x. We have a binary search tree, follow the search path for it. And we know how long it's going to take now, because we know that no matter what we look for, the expected length of the search path is only 2 times the natural logarithm of n plus 2, at most that, which means that as long as we make sure that the thing we have is a random treap, then find is going to work in O of log n expected time. just by the fact that it's a random treap and the fact that random treaps have this bound on the expected length of a search path. So find is easy if we can maintain a random treap. But the trick is maintaining a random treap as someone is adding and removing things from it. So let's see how we could do this add operation. So I'm going to make a small example. Maybe we can use different colors for the keys. So let's put here 5, 3, 2. Over here we'll put 10, 8, and 15. Okay. So there's a picture of a treap. And I'm going to pretend it's a random treap by pretending that these numbers that I wrote here, 0.1, 0.3, 0.2, and so on, that those were chosen at random to go with those keys. Okay? So you think of this as we've been maintaining this data structure for a while, and now it looks like this. And now someone comes along and says they want to add something. So remember that a sorted set has no notion of priorities. So the thing that they want to add is some value x. And so maybe, for example, they want to add the value 9. Okay? All right. So you say, well, that's easy. I know how to add things to a binary search tree. So I just do that. I start at the root. 9 is bigger than 5. 9 is smaller than 10. 9 is bigger than 8. And then I fall out of the tree. And I say, okay, good. 9 goes here. That was easy. But now you're probably saying, hey, wait a minute, there's something wrong. You don't have a treap anymore. Why don't you have a treap anymore? Well, because you don't have a priority at this node. Okay. And so then you'll say, all right, so let's put a priority at this node. Well, we want something bigger than 0.4, so let's put 0.6. Good, done. Now it's a treap. Hopefully, somebody is suspicious that it's that easy. So what's wrong with this? Well, what's wrong with doing this is, so why did I pick 0.6? I picked it because it was bigger than 0.4, and I need a priority that's bigger than the priority at the parent. What's wrong with this is this priority is not random. I didn't pick it randomly. I picked it by looking at some other priority and picking something bigger. Okay. So that doesn't work. And why do I need this priority to be random? I need the priority to be random because this thing here, this theorem about the length of the search path, is only true for random treaps, not treaps that have priorities like this in them that are just larger than the previous one. So, okay, so that doesn't work. Picking this priority larger than the previous one doesn't work. So instead, I'll pick a random real number between 0 and 1. And of course, if you pick a random real number between 0 and 1, you'll get a number whose decimal expansion is infinite. There's more irrational numbers. So that's not so good. But I'll pretend that the number 0.33 is a random real number. let's say I'm going to pretend that I picked a random real number between 0 and 1, and I got 0.33. All right, good. You might say, all right, now we're done, finally. It has a random priority. And again, you should think, well, that's too easy. Now we have another problem. Yes, all the priorities are, if they were random before, they're still random because the only one I added is a new random one. But this thing is not a treap anymore. And why is it not a treap? Well, it's not a treap because there's exactly one place where it doesn't satisfy the heap property. Here I have a priority of 0.33, and its parent has a priority of 0.4. That's not allowed, right? The parent's priority is supposed to be smaller than the child's priority. So I need to fix that. Okay? So somehow I need to reverse the roles, the child-parent relationship between these two nodes. So if I call this node y, and I call this node x, I have a picture where x is the parent of y, but what I want is a picture where y is the parent of x. We have a picture like that over here. Here's a picture where x is the parent of y, and if I do a left rotation, I convert it to this thing where y is the parent of x. Okay. And this picture is valid even if these trees A, B, and C are empty, which is what you may not have recognized it, but that's what's happening here. There are still, we can imagine there are still subtrees here. Here's where A would be, here's where B would be, and here's where C would be. They just happen to be empty. So I can do a left rotation of these two things. And here's where I'm likely to lose data, so let me do some copying first. Although I guess I could just rewind the video and see what was there if I lost it. That would be a little bit too meta, though. 0.339. So 0.339. So now I have y up here and x down here. So these were in the wrong order before. X was the parent of y. I wanted it the other way around. So I just do a rotation that changes the relative order of those things. If there were subtrees attached to this, they would still be attached. So, all right, and now this edge, which was causing me grief, the one that joins the node with priority 0.33 and the one that joins the node with priority 0.4, is no longer violating the heap property anymore. The one with smaller priority is the parent of the one with larger priority. Now, so now we're done, but we're only done in this particular example. And we're only done now because the priority that I picked here was 0.33, and the priority up here is 0.2. If I had picked something smaller, like let's imagine instead of picking 0.33, I had picked 0.15, then I would not be done. I still have a problem because the heap property is fixed here, but now it's broken here between these two. But that's okay. because I know how to fix it. So now I can imagine, let's call this node X, this node Y. X is a child of Y, and I want it to be the other way around. That looks like this picture. X is a child of Y, and I want it to be the other way around with X a parent of Y. So I can do a right rotation. You only need to rotate if the randomly generated priority has smaller priority than that of its parent. Right? Remember, we're thinking of a min heap, meaning the smaller priorities are closer to the root. The smallest one is at the root. So here, with this priority, I would not be done yet. I need to do the rotation, and here's where for sure I will mess it up. But let's try it anyway. So first let me copy out this one, 0.2 and 10. And well, this one is going to go 0.15, 9 is going to go there. That one is its right child. And this one has as its right child 15. Okay. So in this picture, when I did this rotation, there was an A and there was a C from these things, but the B is still missing. There's no value. There's an empty subtree here. Okay. But that's still a rotation like in that picture. It just so happens that B is an empty subtree. Okay. All right, good. And now if you need to, you keep going, right? If this thing is still smaller than the priority, so that fixes this. 0.15 is smaller than 0.2, so that's good. The only possible problem is between this newly added node and its parent, and if you need to, you do the rotation to swap it with its parent. So, so the algorithm is you just add the thing as a leaf, you give it a random priority, and as long as its priority is smaller than that of its parent, you rotate it so that it replaces its parent. You keep doing that until this thing lands in the right place. In this example, we managed to do it after 2 rotations. This thing finished in the correct place. All right, that's good. So, how long does that take? So what is this? Well, we do a search in the binary search tree. We add a leaf, and then do some rotations. And each rotation brings the node that we've just added closer to the root. Okay. So let's think about how long this takes. The search is just, the time that takes has to do with the length of the search path. But that's order log n. Adding a leaf, that's just constant time. We just create a new node and we attach it. That's just changing a pointer. So that's constant time. And then we have to do a bunch of these rotations. How many of these do you do? Well, it's hard to figure that out exactly, at least in this course, because we have a random tree and we just did a random treap. We picked a random priority. We had to keep going until this thing got to the right place in the treap. I have no idea how many rotations that's going to take, but one thing that I can tell you is each rotation brings it closer to the root. And if the thing makes it all the way up to the root, then for sure you stop, because then that just means it has the smallest priority. It had to go, it was the smallest one, and it stops at the root. So if each time I rotate, I get closer to the root, that means that I can't rotate more times than the length of the search path. Right? Because the length of the search path tells me how far the first node, when I add the node, how far it is from the root. After that, each time I do a rotation, I bring it closer. So the number of rotations is not more than the length of the search path, which is only O of log n. And a rotation is not a difficult thing, at least conceptually, right? It's just changing a few pointers that are stored in the nodes x and y. It doesn't touch the rest of the tree. So there's only maybe 6 pointers you would have to worry about there. The parent and left and right child pointers of both x and y. In fact, 2 of them don't even have to change, as you can see from this picture. So maybe it's a tricky bit of code, but it's only like 5 lines of code. It's not a complicated thing. Okay, so that means already we can add things to a random treap, and if it was a random treap before we added it, meaning all the priorities were chosen at random, the new thing that we add has a random priority. That's the way we define it. We pick a random priority for it. Then we do the rotation so that the thing becomes the treap again, the only treap it could possibly be with those priorities and those keys. And that means it's a random treap again. It's a random treap on n+1 elements now. Okay. All right, this is dangerously close to done. All we have left is one operation, the remove operation. So let's think about how we could do that. Let's try an example. Let's remove 15 from this treap. Okay, so to remove it, I need to find it first. So I find it. Here it is. It's a leaf in the treap. Okay, so what if I just cut it out? Okay. So now it's not referenced, it's not part of the treap anymore, and it's gone. Let me quickly run through my head and see, did I break anything here? Is this thing does this thing still have the heap property? For sure it does, because all I did was take away an edge. All the other edges are still the same, right? They're still between the same nodes, so they don't violate the heap property, because they didn't violate it before. They had it before, so that's fine. Is it still a random treap? Yeah, all the priorities were random before, and I didn't change any of them in any way, so they're still random. So yeah, this is now, after removing this node, I still have a random treap, but now it's a random treap on n-1 nodes. Okay, but maybe that was too easy. So removing 15 from this thing was easy. And why was it easy? It was easy because 15 was a leaf. So 15 didn't have any children, so it was kind of easy to remove. We just cut it out. But if 15 had children, then we couldn't just cut it out, because then we'd lose these children from the treap too. Let's try something harder. In fact, let's try the hardest thing we could imagine. What if we want to remove 5? So 5 is at the root. So I can't just cut 5 out of this tree, because then I'll be stuck with 2 trees. That's not good. So I need some more clever thing to do. Well, I know that it was easy to remove leaves, so maybe I should try to make 5 a leaf in this tree. Somehow do something so that 5 becomes a leaf. Well, how could I make 5 be a leaf? Well, 5 is up here at the root, and leaves should be further down. So I want something that pushes 5 down in the tree. Well, what pushes 5 down? Well, these rotations will do that, right? Here, the node X, if I do a left rotation, it moves down in the tree. Here, the node Y, if I do a right rotation, it also moves down in the tree. So if I want to take 5 and push it down towards the leaves, I can just do a rotation. In fact, left or right, either one of those will push it down. Now, the question though is, well, if I have 2 choices, which one should I use? And you might look at the picture and say, oh, I'll push it down on the left side because somehow that's closer to the leaves. You would be right, but your reasoning would be wrong. When you do a rotation, if I do a right rotation, that means that this one will become the new root. If I do a left rotation, that means that this one will become the new root. If we think about it for a second, we don't actually get to choose which one is going to be the new root. The new root has to be the one with smallest priority. So we have this node, we look at its 2 children, one of those 2 has the smaller priority, and that determines whether we should do a left rotation or a right rotation. In this case, we should do a left rotation because we want the new root to be the priority 0.15. So we do that rotation. Now the picture is going to blow up for sure. That means over here. What did I used to have? This was a 5 and a 0.1. This thing's going to go away. That's over there, and that's down there. Yeah, this is a 9. Okay. So that's the right rotation, or the left rotation, the correct rotation to bring this thing closer to being a leaf. But it is still not a leaf. It still has 2 children, in fact. So I'll need to do another rotation to make it closer to being a leaf. And is it going to be a right rotation or a left rotation? Well, it's going to be a right rotation because that will make this thing the new, that will make this thing the new parent, right? It has to be the smaller of the 2 that comes up. And so I do that. And yes, I realize my nodes are starting to look like potatoes, but that will get better in a second. And we get a picture like that. And now, this thing is still not a leaf. I still have to do a rotation, but now I don't really have a choice anymore because, so just to be accurate, this thing should be the right child of this node. There's no option This thing only has a right child, so I have to do a left rotation. And when I do that, I will finally finish with 8. And now finally, the thing that used to be the root, key value 5 with priority 0.1, has finally been pushed all the way down until it becomes a leaf, and then it's easy to remove. Just cut this link, and it's gone forever. Okay. So when you want to remove something, you find it. If it's a leaf, you just cut it away. Otherwise, you will do a series of rotations, each one making it further away from the root until it becomes a leaf, and then you can cut it away. And whether or not you do a left rotation or a right rotation just depends on whether the left child or the right child has smaller priority. In fact, you want to invert that completely. So you want the child with smaller priority to replace the node that's being pushed down. All right. So that's how removing works. And let's just quickly analyze that. Well, what does the remove operation look like? So when we remove, we search for x. We have to find the node that contains the value we want to remove. But that's okay. We know that that only takes O of log n time. Then we have to do a sequence of rotations until x is a leaf. And then finally we cut x out of the tree. So the search for x, we've already figured out that only takes O of log n expected time. Cutting x out of the tree, that's just changing 2 pointers. So that's only constant time. But this sequence of rotations that we do, so here we did a bunch of rotations that pushed this thing down in the tree until it became a leaf. How many of those do we have to do? And that actually, that's one that I really don't understand. Without seeing a trick, this is really not easy to understand. In fact, the reason that this is tricky to understand is, okay, so you might say, well, what if we know the height of the tree is small? Like, maybe the height of the tree is log n, although this doesn't quite say that, but close enough, let's pretend. Then, well, maybe the number of rotations you do can't be more than the height of the tree, because each time you do a rotation, it's getting further from the root. So you shouldn't do more rotations than the height of the tree. But there's a problem with that argument. And you can actually see the problem here, for example. Let's say that I'm doing a rotation to push this node down. Okay. Well, what's the height of the tree? Well, in this case, the height of the tree is somehow determined by the height of this subtree here, the subtree C. Right? C is a tall tree. Somehow it's the tallest one. And if I look at what happens after I do the rotation, the height increased, right? To get to C, I used to only have to go through Y. Now I have to go through X and Y. So the height of C increased by 1. And so, yeah, Y is trying to get down to the leaves, but this rotation, in this rotation, the leaves are somehow running away from y. So that's not good. That's not a good argument to say that it's even the height of the tree, because the height of the tree could keep increasing every time you do a rotation. But here's what makes it easy to understand, and you see it in this picture. What happens, imagine I do the deletion, so I know eventually it will finish because certainly each time its distance from the root increases, and it can never get to be more than n minus 1, because that's the maximum height of a tree with n nodes. So eventually you reach a picture like this where you get to cut it out. And now look at what happens after you've cut it out. Okay. So what is this thing? After you've cut it out, this is a treap, random treap on n minus 1 nodes. Right? Now imagine that I made a video. In fact, you have a video right there. You can rewind it if you like. Imagine that I made a video of me deleting this thing from the tree. So all the rotations that pushed it down, pushed it down, pushed it down until it became a leaf. And now I play that video backwards. So I start at the end where this is already a leaf, and I play it backwards. So rotations are reversible, right? This reverses this. So when I play the video backwards, I see a sequence of rotations. And each of those rotations is bringing this thing up higher in the tree. In fact, if I play the video backwards, the video looks exactly like I had just inserted this thing into this tree with this priority. Okay? So the point is, the time it takes to do a deletion on a tree with n nodes is actually the same thing as the time it takes to do an insertion on a tree with n minus 1 nodes. Right? If I play the video backwards or forward, if I play it at the same speed, it takes the same amount of time. It's just that if I watch it backwards, it looks exactly like I'm inserting this node in a tree of size n minus 1. So that means that this remove thing runs in exactly the same time as adding, except you replace n with n minus 1, because it's like you're adding to a tree of size n minus 1, but it's exactly the opposite operations you would do if you were doing that. Okay. And so finally, that gives us our theorem about random treaps. In the book, this is just called the treap, and that is that a treap implements the S-set interface, and each of add x, remove x, and find x runs in O of log n expected time. Okay. So for you guys, this is sort of the first balanced binary search tree that you've seen. So the first thing that supports adding and removing, a binary search tree that lets you add and remove things and somehow lets you do all these operations in log n time. So these are, as far as this sort of classic data structures are, these are fairly new. And these are really simple algorithms, right? If you look at the code in the book, they're only a few lines long. If I had a blackboard, I would have actually tried to write out the pseudocode for these things. They're super simple algorithms that, again, even if you don't know the analysis, in particular if you don't know how to prove that theorem about random binary search trees, if you went away after this class with nothing but your laptop and no access to internet, there's still a very good chance that you'd be able to implement one of these treaps. Okay? That you would be able to remember enough, basically all of the details, so that you could implement this thing and get it done. That's a fairly new phenomenon. 20 years ago, 30 years ago, there weren't balanced binary search tree data structures that were that simple. In fact, we'll see when we look at red-black trees, the kinds of nightmares that you get when you try and do this without using randomization or some other clever trick or amortization. That you get really complicated structures that are difficult to remember, difficult to understand, difficult to implement. And so it's lucky for you guys that you're growing up in this great time when there's these simple structures to understand. Okay, so that's it for today. I can take questions for a couple of minutes. So it seems like not a lot of questions. I suspect that's because most people in this class are thinking about the exam that they have to write in less than 10 minutes. So for those of you who showed up, thanks for showing up. And I will talk to you on Friday.